Okay, exercise 40. Prove that n cubed minus n is always divisible by 3. Okay, so actually we proved this in our first tutorial using one method. Right here, we're going to use mathematical induction to prove it. Okay, to prove it. So again, mathematical induction, 2 parts. First part is basic step. You have to prove n cubed minus n is divisible by 3 when n is 1. Okay, how to do that? Very easy. You substitute 1 for n, right? You let n to be 1, then n cubed minus n is 1 cubed minus 1 is 0. Okay, and 0 is divisible by 3. So when n is 1, it is true. Okay, so when n is 1, it is true. Then let's assume it is true when n is k. Then we prove it is also true when n is k plus 1. Okay, so we assume it is true when n is k, which means k cubed minus k is divisible by 3. Okay, we assume this is true. Then we want to figure out when n is equal to k plus 1. What about k plus 1 cubed minus k plus 1? Okay, what about k plus 1 cubed minus k plus 1? So k plus 1 cubed, right, is k cubed plus 3k squared plus 3k plus 1. Okay, minus k minus 1. Okay, minus k minus 1. So you simplify it and you regroup them. Okay, you simplify this equation and you regroup them. You will see 2 parts. Okay, first part is k cubed minus k. K cubed minus k. Second part is 3 times k squared plus k. Okay, is 3 times k squared plus k. So they are both divisible by 3. Okay, the second part is divisible by 3 because it's 3 times something. Okay, so 3 times k squared plus k is obviously divisible by 3. The first part, k cubed minus k, is divisible by 3. It's because just now we assumed it, right? We assumed k cubed minus k is divisible by 3. Okay, so both parts are divisible by 3, then their sum is divisible by 3. Okay, so we have done the inductive step. If n is k, it is true, then n is k plus 1 is also true. Okay, so this is true, right, using mathematical induction. Okay, using mathematical induction. So, then the last one, right? Last one, exercise 41. Prove by mathematical induction that 1 squared plus 2 squared plus all the way to n squared is equal to 1 over 6 n times n plus 1 times 2n plus 1. Okay, so you want to prove this equation is true for all positive integers n. Okay, for all positive integers n. So again, we prove it's true, right? We prove the basic step, then we prove the inductive step. Okay, in the basic step, we need to prove when n is 1, it is true. Okay, so how to do that? Again, the same, right? You substitute 1 for n on the left side as well as on the right hand side. Okay, on the left hand side, it's just 1 squared. Okay, on the right hand side, it will be 1 over 6 times 1 times 2 times 3. Okay, so it will also be 1. Okay, so when n is 1, the left is equal to the right. So the statement is true. Okay, so the statement is true. Inductive step. Okay, suppose when n is k, it is true. Okay, suppose when n is k, it is true. So 1 squared plus 2 squared plus all the way to k squared is equal to 1 over 6 k times k plus 1 times 2k plus 1. Okay, we assume when n is k, it is true. Okay, then when n is k plus 1, when n is k plus 1, it is 1 squared plus 2 squared plus all the way to k squared plus k plus 1 squared. Okay, for the first part, for the 1 squared plus all the way to k squared, right, we already assume it is 1 over 6 k, k plus 1, 2k plus 1. Okay, so we can replace the first part. We can replace 1 squared plus 2 squared plus all the way to k squared. We can replace it with 1 over 6 k times k plus 1 times 2k plus 1. Okay, then plus k plus 1 squared. Okay, then there's a common factor k plus 1, right? There's a common factor k plus 1. Okay, so we put the common factor k plus 1 out. So it becomes 1 over 6 times k plus 1 times the first part is k times 2k plus 1. The second part is plus 6k plus 1. Okay, then you just need to do some algebra, right? You can see that these parts in the bracket, they can be eventually written as 2k plus 3 times k plus 2. Okay, they can eventually be written as 2k plus 3 times k plus 2. And now, when n is k plus 1, right? Here, you see k plus 1 is n. K plus 2 is n plus 1. And 2k plus 1 is 2n plus 1. Okay, so when n is k plus 1, the sum is still equal to 1 over 6 n times n plus 1 times 2n plus 1. Okay, so the equation is still true when n is k plus 1. Okay, so you have proved the inductive step. Okay, you have proved the inductive step. So you've proved the basic step when n is 1 it is true. Then you have proved the inductive step. So you assume when n is k is true. Then you have proved that when n is k plus 1 it's also true. Okay, so this statement is true by mathematical induction. Okay, so this statement is true by mathematical induction.